Hello everyone, good morning. Today we are going to talk about enzymology. Okay, I'm Dr. Shreya Nigoskar, Professor in the Department of Biochemistry. We are going to talk about enzymology. Now, there are specific learning objectives by this learning this enzymology. You can answer, describe isoenzymes, their properties and clinical usefulness, enumerate enzyme markers in various diseases, interpret the laboratory values of enzyme assays in different diseases in diagnosis, prognosis, monitoring, list therapeutic uses of enzymes, describe the enzyme-based diagnostic techniques and uses of immobilized enzymes. Now we are going to talk about isoenzymes. Isoenzymes, they are physically distinct forms of same enzyme's activity. Different molecular forms of some enzymes synthesized from various tissues are called isoenzymes. Hence, study of isoenzymes is very useful to understand diseases of different organs. If the subunits are all the same, the protein is a homomultimer represented by a single gene. If the subunits are different, the protein is said to be a heteromultimer produced by different genes. Now, isoenzymes may be formed in different ways. They may be products of different genes, more than one locus, in which case they are known as true isoenzymes. The genes may be located on different chromosomes, example salivary and polypeptide amylase. In certain cases, all the different forms are present in the same individual. Example, lactate dehydrogenase has 5 isoenzymes, and all the are seen in all persons in the population. Now, isoenzymes may be formed in different ways. The same locus of the gene may have different alleles, alternate forms. Such allelic isoenzymes are called allozymes. In this case, only one form will be present in one individual, but all the different forms will be seen in total population. For example, more than 400 distinct forms of glucose 6-phosphate dehydrogenase have been identified. All of them are produced by same locus on the X chromosome. When isoenzymes, due to variation in at a single locus, occur with appreciable frequency, more than 1% in population, it is said to be polymorphism. Molecular heterogeneity of enzymes may also be produced after the protein is synthesized, post-translational modification. These are called isoforms. Example, sialic acid contained in alkaline phosphatase, ALP isoenzymes. Different types of isoforms may be seen in the same individual. Identification of isoenzymes. In electrophoresis, the isoenzymes have a different mobility. LDH and CK isoenzymes can be separated by electrophoresis. Heat stability. One of isoenzymes may be easily denatured by heat. Example, bone isoenzymes of ALP. That is also called as bar. In inhibitors, one of the isoenzymes may be sensitive to one inhibition. Example, tartrate label ACT. The KM value or substrate specificity may be different for isoenzymes. Example, glucokinase has high KM and hexokinase has low KM for glucose. Cofactor requirements may be different for isoenzymes. Mitochondrial isocitrate dehydrogenase is NAD plus dependent, and the cytoplasmic isoenzyme is NADP plus dependent. Tissue localization may be different for isoenzymes. H4 form of LDH is present in heart, while M4 variety is seen in skeletal muscle. Specific antibodies may identify different types of isoenzymes. For example, CK isoenzymes are separated by antibodies. Isoenzymes of LDH. Lactate dehydrogenase enzyme is a tetramer 4 subunits. But the subunit may be either H, heart, or M, muscle, polynucleotide chains. So 5 combinations of H and M chains are possible. These combinations are H4, H3M1, H2M2, H1M3, M4 varieties. All these 5 forms are seen in all persons. So you can see the electrophoresis pattern of LDH isoenzyme. This is H4, H3M1, H2M2, H1M3, and M4. This is point of application. And this you can see the pattern. Like this. Okay, so we have to remember the pattern. And if there is a question on isoenzyme, you can just draw it and no more than this about you can write it, express yourself in writing. Characteristic features of LDH isoenzymes. Subunit makeup of isoenzyme like this is H4, H3M1, H2M2, H1M3, M4, and electrophoretic mobility at pH 8.6. It is the H4 is the fastest. And activity at C at 60 degrees centigrade for 30 minutes is not destroyed. And tissue of origin is heart muscle. And percentage in human serum is 30%. H3M1, it is faster. It is also not destroyed. The tissue of origin is RBC and brain, and the percentage in human serum is 35%. Now H2M2, the electrophoretic mobility is fast, then it is partially destroyed, and it is synthesized for tissue of origin is brain, leukocytes, and percentage is 20% in human serum. Now H1M3, the mobility is slow, it is also destroyed, and liver it is synthesized, or it is the tissue of origin is liver and leukocytes, and percentage in human serum is 10%. M4, the mobility is slowest, it is totally destroyed. At this activity is not there, it is destroyed, and it is the origin is tissue of origin is skeletal muscle, and only 5% is present in human serum. Okay, so this is about the characteristic features of LDH isoenzyme. Now, M4 form is seen in skeletal muscle, while H4 form is seen in heart. Normally, H3M1 concentration in blood is greater than H4, but this pattern is reversed in myocardial infarction. This is called flipped pattern. LDH level is 100 times more inside the RBC than in plasma, and therefore minor amount of hemolysis will result in a false positive test. Since total LDH is increased in many conditions, LDH is also LDH is not used as a cardiac marker nowadays. Previously, it was a cardiac marker, but nowadays it is not used as a cardiac marker. Now, clinical enzymology. Plasma contains many functional enzymes which are actively secreted into plasma. For example, enzymes of blood coagulation. On the other hand, there are a few non-functional enzymes in plasma which are coming out from cells of various tissues due to normal wear and tear. Their normal levels in blood are very low but are drastically increased during cell death, necrosis, or disease. Therefore, assays of these enzymes are very useful in diagnosis of diseases. Now, next one, that is biomarker. A biomarker is defined as one naturally occurring molecule, gene, or characteristics by which a particular pathological process can be identified. Another definition is that a biomarker is a substance used as an indicator of presence of a material of biological origin or a physiological condition or process, specifically a diagnostic indicator of predisposition to a medical condition. Next one, that is cardiac biomarkers. These cardiac biomarkers are these may be classified as cardiac markers of myocardial infarction, markers of risk prediction, markers of myocardial stress or congestive cardiac failure. Commonly used biomarkers are early detection of acute myocardial infarction are cardiac troponin, is TN1, TNI, and TNT, and creatine kinase isoenzyme CK, NV. The brain natriuretic peptide is a useful indicator of congestive cardiac failure. Now, alanine aminotransferase is also known as ALT. Normal serum level of ALT for male is 13 to 35 units per liter, and for female it is 10 to 30 units per liter. Very high values, that is 300 to 1000 units per liter, are seen in acute hepatitis as a toxic or viral in origin. Both ALT and AST levels are increased in liver disease, but ALT and AST, but ALT is more than AST. Rise ALT levels may be noticed several days before clinical signs such as jaundice are manifested. Moderate increase by 50 to 100 units per liter of ALT may be seen in chronic liver diseases such as cirrhosis, hepatitis C, and non-alcoholic steatohepatitis. Aspartate aminotransferase or AST. Reference serum levels of AST ranges from 8 to 20 units per liter. It is a marker of liver injury and shows moderate to drastic increase in parenchymal diseases like hepatitis and malignancies of liver. AST was used as a marker of myocardial ischemia in olden days. The level of is significantly elevated in myocardial infarction. As AST is raised in various other conditions, the troponins have replaced AST as a diagnostic marker in ischemic heart disease. AST is now used as a marker for hepatic injury. Alkaline phosphatase, ALP. ALP hydrolyzes aliphatic, aromatic, or heterocyclic compounds. pH optimum for enzyme reaction is between 9 to 10. It is activated by magnesium and manganese. Zinc is a constituent ion of ALP. It is produced by osteoblasts of bone and is associated with the calcification process. Moderate 2-3 times increase in ALP level is seen in hepatic diseases such as infective hepatitis, alcoholic hepatitis, or hepatocellular carcinoma. Now, alkaline phosphatase. Very high levels of ALP, that is 10 to 12 times of upper limit, may be noticed in extrahepatic obstruction, obstructive jaundice, caused by gallstones or by pressure on bile duct by carcinoma of head of pancreas. Intrahepatic cholestasis may be used, maybe due to virus or infective hepatitis or by drugs like chloroform and G. LP is produced by epithelial cells of biliary canaliculi and obstruction of bile with consequent irritation of epithelial cells lead to secretion of ALP into serum. Drastically high levels of ALP, that is 10 to 25 times of the limit, are seen in bone diseases where osteoblastic activity is enhanced, such as Paget's disease, rickets, osteomalacia, osteoblastoma, metastatic carcinoma of bone. Isoenzyme of alkaline phosphatase alpha 1 ALP moves to alpha 1 position. It is synthesized by epithelial cells of biliary villi. It is about 10% of total activity and is increased in obstructive jaundice. Alpha 2, that is heat labile LP, is stable at 56 degrees centigrade, but loses its activity when kept in 65 degrees for 30 minutes. It is produced by hepatic cells. Isoenzyme of alkaline phosphatase. Alpha 2 heat stable LP will not be destroyed at 65 degrees but is inhibited by phenylalanine. It is a placental origin. It is of placental origin which is found in blood in normal pregnancy. An isoenzyme closely resembling the placental form of is characteristically seen in circulation is about 15% cases of carcinoma of lung, liver, and gut, and named as Regan isoenzyme or carcinoplacental isoenzyme. 3-beta LP is of bone origin and elevated levels are seen in bone diseases. This is heat labile destroyed at 56 degree for 10 minutes when kept at 56 degree for 10 minutes. Heat labile bone isoenzyme of alkaline phosphatase, that is BAP, is a marker for bone disease. Now, specific antigen. Prostate specific antigen is produced from the secretory epithelium of prostate gland. It is normally secreted into seminal fluid, where it is necessary for liquefaction of seminal curriculum. It is serine protease and is a 32 kD glycoprotein. In blood, it is bound to alpha 2 microglobulin and alpha 1 antitrypsin. A very small fraction is in the free form also. Reference serum value is 1 to 5 units per liter. It is very specific for prostate activity. Values above 10 units per liter is indicative for prostate cancer. Now, acid phosphatase. Acid phosphatase ACP hydrolyzes phosphoric acid ester at pH between 4 to 6. Reference serum value of ACP is 22.5 to 12 units per liter. ACP is secreted by prostate cells, RBC, platelets, and WBC. The prostate isoenzyme is inactivated by a tartaric acid. Normal level of tartrate labile fraction of ACP is 1 unit per liter. ACP total value is increased in prostate cancer and is highly elevated in bone metastasis of prostate cancer. In these conditions, our tartrate labile isoenzymes are elevated, and this assay is very helpful in follow-up of treatment of prostate cancer. So ACP is an important tumor marker. Since blood cells contain excess quantity of ACP, care must be taken to prevent hemolysis while taking blood from patient. Now, cholinesterase, CH. Acetyl cholinesterase or true CHE or type 1 CHE can act mainly on acetylcholine. It is present in nerve endings and in RBCs. Newly formed RBC will have high levels of CHE, which is slowly reduced according to the age of the cell. Therefore, CHE levels in RBCs will be proportional to the reticulocyte count. Organophosphorus insecticides irreversibly inhibit CHE in RBCs. Measurement of CHE level in RBCs is useful to determine the amount of exposure in persons working with these insecticides. Now, glucose 6-phosphate dehydrogenase. It is an important enzyme in the hexose monophosphate shunt pathway of glucose. It is mainly used for the production of NADPH. Hydrogen peroxide is the continuously formed inside the RBCs. Peroxide will destroy RBC cell membrane. Glutathione and NADPH will prevent this process. Therefore, NADPH is very essential for preserving the RBC integrity. Okay. Drug-induced hemolytic anemia. In the GPD deficient individuals, RBC lifespan may be reduced, but there will be no disease manifestations. But when certain drugs like aspirin, like mepacin, sulfa are taken by such individuals, there will be sudden damage to RBCs. Primaquine stimulates peroxide formation. Now, in GPD deficient cells, the level of NADPH is low, leading to unchecked buildup of peroxides, resulting in premature cell lysis. This drug-induced hemolytic anemia is characteristic of GPD deficiency. Fava beans like star beans, corner beans may also induce hemolytic anemia, which is called as fabicin. Okay, you have to remember all these things. So, the gene for GPD is located in X chromosome. Therefore, hemizygous males and homozygous females will manifest the disease, while heterozygous females are carriers. In heterozygous condition, where one gene is abnormal and a weak form is normal. The GPD level in RBC is half the normal value. GPD deficiency seems to protect the person from falciparum malaria. The malarial parasites require NADPH for optimal growth. Thus, GPD deficiency has a selective advantage in malaria infested regions. Okay, it is very important thing to be remembered. Methemoglobinemia. NADPH is also necessary for reduction of methemoglobin. Oxidized methemoglobin is oxidized to hemoglobin. Okay, NADPH is also necessary for reduction of methemoglobin to hemoglobin. Hence, in GPD deficient individuals, methemoglobinemia may also be manifested. Okay. So, next one. Carrier state has biological advantage. The gene for GPD is located in X chromosome, therefore hemizygous males and homozygous females will manifest the disease. Okay. Now, next one, that is amylase. Amylase is enzyme splits starch to maltose. It is activated by calcium chloride ions. It is produced by pancreas and salivary glands. Reference serum value is 50 to 120 international unit per liter. The value is increased about 1,000 times in acute pancreatitis, which is life-threatening condition. Pancreatitis, life-threatening condition. The peak value are seen between 5 to 12 hours after the onset of disease and returns to normal levels within 2 to 4 days after the acute phase has subsided. Moderate increase in serum levels are seen in chronic pancreatitis, mumps, which is also called as parotitis, and obstruction of pancreatic duct. Reference value of amylase in urine is less than 375 units per liter. It is increased in acute pancreatitis. It is increased on the first day and remains to be elevated for 7 to 10 days. Now, next enzyme, that is lipase. It will hydrolyze triglyceride to beta monoglyceride and fatty acid. The enzyme is present in pancreatic secretion. The level of blood is highly elevated in acute pancreatitis. It's very important. temporarily, and it persists for 7 to 14 days. Thus, lipase remains elevated longer than amylase. Moreover, lipase is not increased in norms. Therefore, lipase estimation has advantage over amylase. It is moderately increased in carcinoma of pancreas, biliary diseases, and perforating peptic ulcers. Now, next enzyme, that is enolase. It is glycolytic enzyme. Neuron specific enolase. Glycolytic, we have studied about glycolysis, so enolase is present here. Phosphoenol pyruvate to pyruvate. Okay, like that. So it is glycolytic enolase is glycolytic enzyme. Non-neuron specific enolase is an isoenzyme seen in neural tissues and acute terminals. NSC is a tumor marker. NSC means neuron specific enolase. It is a tumor marker for cancers associated with neural endocrine origin. Small cell lung cancer, neuroblastoma, pheochromocytoma, medullary carcinoma of thyroid, etc. Next is ceruloplasmin. It is otherwise called peroxidase. Reference serum level is 25 to 50 milligrams per deciliter. Modern techniques based on radial immunodiffusion or immunoturbidimetric methods are also available. Since it is an acute phase protein, it is increased in all inflammatory conditions, collagen diseases, malignancies, and pregnancy. A value less than 20 milligram per deciliter is preferred like this. A value less than 20 milligram per deciliter is pathognomonic of Wilson's hepatolenticular degeneration, in which copper toxicity is manifested. Now, enzyme pattern or enzyme profiles in diseases. Various diseases in which enzyme pattern can be seen for the diagnosis and therapeutic purposes. So, enzyme patterns in diseases we discuss here. Various diseases with various enzymes which are very important to remember. No. So, hepatic diseases. Alanine aminotransferase is also known as ALT. Marked increase in parenchymal liver diseases. And second one, that is aspartate aminotransferase, AST, elevated in parenchymal liver disease. Third one, alkaline phosphatase, ALP, marked increase in obstructive liver disease. Fourth one, gamma glutamyl transferase, GGT, increase in obstructive and alcoholic liver. Okay, this is about hepatic diseases. Second one, that is myocardial infarction. Cardiac troponins, CTNT and CTNI. These are not enzymes, but are specific and sensitive and elevated very early in myocardial infarction. Second one, creatine kinase. We know that there are 3 isoenzymes for creatine kinase. So one of them is CKMB. CKMB, it is an enzyme which is specific for myocardial infarction. Next disease, that is muscle diseases, in which first one, that is creatine kinase. Again, one of isoenzymes, that is CKMN, marked increase in muscle diseases. Second one, aspartate aminotransferase, AST, increase in muscle disease but not specific. Allolase, ALD is earliest enzyme to rise but not specific. Okay, these are the various enzymes to be remembered in these diseases. Now, next slide, that is next one, that is bone diseases, alkaline phosphatase, ALP, marked elevation, rickets and Paget's disease. And next, that is prostate cancer. Prostate specific antigen PSA, marker for prostate cancer. Mild increase in benign prostate enlargement. Second one, that is acid phosphatase, marker for prostate cancer. Metastatic bone disease, especially from primary form prostate, inhibited by L-targeted. Okay. Next one, that is pancreatic disease. First one is amylase. Amylase, it is a marker for acute pancreatitis and inflammation of salivary glands. Second one is lipase, marker for pancreatitis, more specific than amylase. Okay. Next one, that is enzyme as therapeutic agents. So we have already discussed about the diagnostic purpose of enzymes. Now therapeutic agents means enzymes, they are also used in the therapy of various diseases. So in these, number one is streptokinase. It is from streptococcus, or urikinase is from urine. Can lyse intravascular clots and are therefore used in myocardial infarction. Okay, so it is very, very primary therapeutic agents for myocardial infarction, streptokinase or urokinase. Next one, that is pepsin and trypsin. They are given to patients with dependency, effective digestion. Pepsin and trypsin. These are again the enzymes which are used for therapeutic purpose for effective digestion. Now, asparaginase is used as an anti-cancer drug. So, streptokinase, pepsin, trypsin, and asparaginase. These are the various enzymes used for therapeutic purpose of various diseases. Next one. Ceruloplasmin. We have studied this. It is also called peroxidase. Okay. It is a kind of diagnostic enzyme. We studied various diseases and diagnostic purpose of enzymes. Therapeutic agents also we have studied. Like these enzymes, streptokinase, pepsin, trypsin, asparaginase, these are used as a therapeutic agents. Now you can draw a chart. If there is a question, like write a short note on therapeutic use of enzymes, then you can draw this chart, and in one column you can write about enzyme, another one therapeutic application of enzyme, therapeutic application of enzyme, and various enzymes with their name and their therapeutic application. So asparaginase is used in acute lymphoblastic leukemia, and streptokinase is used to lyse intravascular clot, and urokinase lyse intravascular clot again. Then next one is recombinant tissue growth hormone activator. It is used for lysis of clot, especially for cerebrovascular thrombolysis. And next one, that is streptokinase DNase. It is applied weekly. Next one, that is pancreatin or trypsin and lipase. Pancreatic insufficiency. It is administered orally, used for oral administration. In Japan, it is anti-inflammatory therapeutic agent. The next one, that is alpha-1 antitrypsin, that is used in AAT deficiency or emphysema. Next one, enzyme used for diagnostic purpose. Again, we have already discussed, but while writing while remembering or while writing the answer in a answer sheet, you can draw again a chart. You can draw the columns in which one you can write an enzyme, another used for testing. And urease is used for testing urea, uricase for uric acid, glucose oxidase for glucose, peroxidase glucose and cholesterol, isokinase used for testing glucose, cholesterol oxidase for cholesterol, lipase for triglycerides, horseradish peroxidase, HRP for ELISA, alkaline phosphatase, again for ELISA, and then restriction endonuclease is used in southern blot, RFLP, in reverse transcriptase. It is used in polymerase chain reaction. Okay, so that's all about therapeutic enzymes, diagnostic enzymes, clinical enzymology. So I wish you all the best. Thank you so much.